Welcome to this session on Introduction to Multilateral Wells, Sub-Module 1 of 2. In this module, we'll explore the fundamentals of multilateral technology. What defines a multilateral well, why operators use them, the technical and economic benefits and drawbacks, and how the industry classifies junction complexity through the TAML framework. In this sub-module, our objectives are clear. First, we'll define what a multilateral well actually is, so we share a common starting point. From there, we'll discuss applications and advantages, looking at how these wells provide both technical and economic value in field development. You'll learn how to identify the key components of a multilateral schematic, the main bore, the lateral, and the junction that ties them together. Understanding these elements is essential before moving on to more advanced design concepts. We'll also introduce TAML, the Technology Advancement of Multilaterals Consortium. We'll explain its role in standardizing approaches across the industry and promoting technology development. Multilaterals can be utilized as a strategy for both new wells, as a multilateral well is defined as a single main bore with more than one horizontal or near horizontal lateral branching from it. These laterals connect back into the main bore, allowing production or injection from multiple reservoir zones using a single surface location. This concept allows us to maximize reservoir contact without drilling multiple wells from the surface. It reduces surface footprint and often improves recovery from complex reservoirs. Refer to the schematic diagram which is taken from oil field review. The main bore is clearly shown with multiple laterals extending outward. Each lateral represents an additional drainage path into the reservoir. Interpreting the image, the vertical section provides access to depth, while the laterals spread horizontally, greatly increasing reservoir exposure compared to a single horizontal well. This visual reinforces the core definition: one well bore, multiple laterals, all tied back into the same system. Having defined what a multilateral is, let's move next to the historical perspective. The very first multilateral well drilled and what it achieved. The very first multilateral well was drilled in Russia back in 1953. This pioneering project set the stage for what would later become a global technology. The well had 9 lateral branches extending from a single main bore, which was a remarkable achievement at the time. The impact was significant. Reservoir exposure increased by 5.5 times compared to a single borehole. This meant far more reservoir contact, which directly translated into higher production rates. In fact, output increased 17 times, an enormous uplift for relatively little added investment. Capital expenditure only rose by a factor of 1.5, so the return on investment was very favorable. This example demonstrates the power of multilaterals. They allow us to multiply production without multiplying cost in equal proportion. On the diagram shown here, you can see the main bore with 9 laterals branching out like the spokes of a wheel. Each lateral intersects different parts of the reservoir, maximizing contact, so from the very beginning, multilaterals showed their potential to improve recovery efficiency. Next, we'll look at why they are not simply 2 wells in one. One common misconception is that a multilateral well delivers the equivalent of 2 separate wells. In reality, the economics and performance are more nuanced. Let's start with cost. Historically, for multilaterals to be considered economically viable, the capital expenditure per additional lateral should not exceed approximately 50% of the base well. That's far lower than drilling a completely separate well. Production uplift is also significant but not linear. Typically, a lateral branch will add between 30 and 60% improvement over a horizontal well, not double the output. This is because reservoir connectivity, fluid dynamics, and drainage efficiency all vary across the formation. Economically, multilaterals tend to improve overall project value by about 40%. That's a strong result, but it highlights why multilaterals must be assessed carefully. They are not a one-to-one substitute for multiple wells. This sets the stage for the next discussion, where we'll weigh both the advantages and disadvantages of multilateral well design. Multilaterals offer both technical and economic advantages. On the technical side, The most obvious benefit is increased reservoir exposure. By drilling multiple laterals from a single main bore, we dramatically increase the length of reservoir contact. Another benefit is improved connectivity to the reservoir, which helps reduce water coning, gas coning, and sanding potential. Because flow is distributed along multiple laterals, pressure drawdown at any one point is reduced. This results in more stable production and better reservoir management. Multilaterals also allow more efficient exploitation of complex reservoirs, particularly where thin, compartmentalized or fractured zones would be uneconomic to reach with multiple conventional wells. On the economic side, we avoid duplicating the cost of a second surface well bore. The same surface facilities, wellhead, casing, and infrastructure serve all laterals. Offshore, this translates into no additional slot use, meaning platforms can be smaller and less expensive. Ultimately, this increases recoverable reserves without proportional increases in surface cost. Now that we've highlighted the benefits, we need to balance the picture by reviewing the disadvantages of multilaterals. While multilaterals provide many benefits, they also introduce new challenges. Technically, well intervention becomes more complicated. Accessing and working in multiple laterals requires specialized tools, and conventional coiled tubing or wireline may not reach all branches. Reservoir monitoring is also more complex. With multiple drainage points, it is harder to measure flow contribution from each lateral, making reservoir management less precise. Drilling risks increase as well. Creating additional laterals introduces higher chances of instability, stuck pipe, or borehole collapse. Another technical issue is well control. When we open new laterals, we create more potential flow paths, which makes controlling the well during drilling more difficult. Added to that, debris from multiple junctions can accumulate and complicate cleanup. On the economic side, multilaterals carry the risk of losing the main bore and lower laterals if problems arise. Because the laterals are connected, one failure can jeopardize the entire well. The technology is also dependent on advanced tools, which raises both cost and reliance on service providers. To overcome these risks, the industry formed the TAML consortium, which we'll discuss next. The Technology Advancement of Multilaterals, TAML, consortium was established to promote efficient development of multilateral technology worldwide. Its goal is to encourage collaboration, share information, and support collective sponsorship of new tools and practices. By creating a forum for dialogue, TAML helps align operators and service companies on standard approaches. This reduces duplication, accelerates technology adoption, and ensures multilaterals can be applied more consistently across the industry. The consortium includes many of the world's major operators and service companies. This broad membership demonstrates the importance placed on advancing multilateral design. The key outcome of TAML's work is the standardized classification scheme, which allows engineers to categorize multilateral junctions by complexity. This provides a common language for project planning and technology selection. Before we look at that scheme, we'll start with the basic nomenclature used to describe multilaterals. To understand multilaterals, we first need to use clear terminology. The main bore is the original well bore drilled from surface to reservoir. From this main bore, a junction is created where a lateral branches off. The lateral is the secondary borehole drilled away from the junction, providing additional reservoir exposure. On the schematic shown here, you'll see these elements labelled. The vertical section represents the main bore, the branching point is the junction, and the horizontal extension is the lateral. This simple schematic forms the basis of all multilateral design, no matter how complex the well. The key takeaway is that multilaterals are always defined by the relationship between the main bore, the junction, and the lateral. This terminology will guide us as we move into the TAML classification levels, which describe how secure and complex the junction is. TAML introduced a 6-level classification scheme to define multilateral wells based on the complexity of the junction. Level 1. The simplest form, an open-hole lateral without mechanical support at the junction. Level 2. The lateral is cased, but the junction remains unsupported. Level 3. Both the main bore and lateral are cased, but but the junction has no pressure isolation. Level 4 adds partial pressure isolation at the junction. Level 5 provides full hydraulic isolation, allowing independent control of each bore. Level 6, the most advanced, featuring complete junction integrity comparable to a conventional cased well. This classification gives engineers a common reference to balance technical requirements with cost. Lower level junctions are cheaper but less robust, while higher level junctions allow complex field development but at greater expense and complexity. Having reviewed the classification system, we can now step back and revisit the module objectives to confirm what we've achieved in this session. Let's return to the objectives we outlined at the beginning. First, we set out to explain what a multilateral well is. We defined it as a main bore with multiple laterals branching from it, and reviewed diagrams to illustrate the concept. We then listed applications and advantages, covering both technical benefits such as increased reservoir exposure and reduced coning, and economic advantages such as fewer slots and reduced surface costs. We identified the key components, main bore, lateral, and junction, in schematic form, reinforcing the standard nomenclature. Next, we introduced the TAML consortium and explained its role in advancing multilateral technology and establishing standards. Finally, we described the 6 TAML levels. With the objectives reviewed, let's close this submodule. That concludes submodule 1 of 2 on multilateral wells. This submodule is now complete. Please proceed to the quiz to test your understanding of the material we've covered. Thank you for your attention, and I look forward to continuing with you in the next session.